Hello, everyone. This is Michael E. Yeaman with another Geology of Sculpting Stone. Today, we're going to talk about Pacific Northwest Granite. Well, as I said before in the past, really, why should you care about the geology of stone? Stone sculpture, as you know, is one of the very first art forms and dates back to the very beginning of art. Therefore, knowing more about the geology of your stone will allow you as stone sculptors to select specific stone types that have a compelling geologic story and history that might be of interest to you and maybe your viewers and potential buyers as well. When you work the stone, knowing more about the history, you can marvel in its color and its texture, composition, and makes it more fun to actually know that information while you're actually working on your piece. And also, you can consider how the sculpture style you chose relates to the science of the stone. You may choose to work that into your pieces. And finally, you can weave together into your final artwork the overall geologic story that actually might enhance your sculpture both for yourself and for potential buyers. So, as usual, our section here on the geology of sculpting stone is divided into three pieces. The stone defined, its geologic descriptions, a little bit more about its properties, historic use, specimen pictures, both large and small scale, and where you can specifically find it today. Also, the geology, we'll talk a little bit about the geology, the descriptions, where it formed and how it formed. In the global paleogeographic setting, what was the world like when it was being formed? And are there any modern analogs of where you might be able to find it today? And then finally, we'll take a look at specific art and architecture made from this stone. So let's jump in and talk about the general description, physical, and some chemical properties and historic use of Pacific Northwest granite. In general, that term is used to describe light-colored igneous rock forming at several localities in Washington State and in British Columbia. And then two specific areas that have been quarried for the Pacific Northwest granite historically are the coastal plutonic belt of central British Columbia coastal area, the Hardy Island area specifically, whose age is about 120 million years old when the granite was placed, and then two spots in Washington State, the Snoqualmie batholith and the Index Pluton, both relatively younger, 18 and 35 million years ago, respectively. And although they differ quite a bit in age, both areas have this uniform light gray granite, which is geologists refer to as granodiorite, and it's associated with subduction of Andean-style tectonic environments, and we'll talk more about what that means in a minute. Quarrying began in both locations in the early 1900s. The Hardy Island material has been used extensively in Canada and the United States, and, for example, used to create the Victorian Harbour seawall because of its durability and attractive appearance. And finally, the Snoqualmie stone has been used, and still is used extensively throughout the Puget Sound region, and especially for major commercial and government buildings. Now, the chemical composition of both or all three of these areas is rather similar. It's on the right here. And you can see, once again, it contains a lot of silicon dioxide, silica, very common material for almost all rocks, but particularly igneous rocks of a granitic area. A little bit of aluminum oxide and iron oxide making up most of the rest of this, and a mixture of a little bit of darker material. That's oftentimes affiliated with magnesium and calcium, and a little bit of sodium, potassium, and a little bit of titanium oxide. So altogether, this is a fairly standard chemical composition for granites. Here are some pictures. Pictures of large-scale pieces of the the Hardy Island quarry, while some of the worked outcrops and prep blocks ready to go, and the Index quarry in Washington State early in the 20th century, and some large of these granitic boulders on the Skykomish River, showing you how they weather as they roll downstream. So let's take a look at some thin sections. And if you recall what thin sections are, they're a thin slice of rock, in this case, a thin slice of the Pacific Northwest granite, which will allow light to shine through them. So if we take a look at the slide on the left, we see four labeled components of the rock as we see through the light of this thin section. One is quartz, and that is mostly the beigey white material here on the rock. Another common component of granite is a mineral called plagioclase feldspar. And then two other common components of granite making up that chemical composition are darker micas called biotite and lighter micas called muscovite. Now, if you take a look at the slide on the right, and it's been exposed now or shining through it, is a type of light called cross-polarized light. And actually, it greatly enhances the differential character and appearance of the quartz down here below. The plagioclase now, which makes up this large crystalline structure here on the left, and the biotite now in a more light yellowish color to the above, and the muscovite being this long linear crystal here in the middle. So in all cases now, the cross-polarized light actually allows mineralogists oftentimes to make some much more significant predictive components of what makes up overall stones. In this case, it allows them to identify the mineralogical components of Pacific Northwest granite much more clearly. Let's take a look at a few specific occurrences now of Pacific Northwest granite. And let's begin with the Index Pluton area, the town of Index, sitting on the Skykomish River. Index is on Highway 2, going from the North Seattle area on into Leavenworth, lovely town up in the mountains. It began a long time ago, early in the 20th century, with John A. Soderberg developing the Index Granite Company, a large quarry that sat on a key railroad track as it came across the Cascades. And during the early 20th century in particular, a lot of men were employed working there full-time, supplying key construction material for buildings throughout the Puget Sound area, including the state capitol. I noticed that's sort of interesting that Soderberg brought workers all the way in from Vermont, another famous granite producing area, working on, among other things, very intricately carved tombstones for use across the United States. Unfortunately, in 1932, the main quarry shed actually burned, and a lot of the stone was destroyed or at least badly damaged, and actually ground and sold as chicken grit way back when. The big thing, however, that really killed a lot of the granite construction business, at least of granite used on a very common building material, was the development of reinforced concrete. After the Depression, with the advent of reinforced concrete, which was far cheaper to create and use than quarried granite, a lot of the demand for granite as a common foundation or building stone went away. And even though the Index Quarry is no longer in operation, a lot of the remnants of it are still around the town of Index and in the Skykomish River. Another location for Pacific Northwest granite, as we mentioned earlier, is Hardy Island, British Columbia. Now, Hardy Island and the quarry is located on the coast of British Columbia up Queen Charlotte Strait. It's a lovely area off of Jervis Inlet, and it was active throughout the 20th century, particularly early 20th century, and it's still being used today. It provided a lot of key building stones for Canada, especially some government buildings, and it's been used in such a wide variety of places as the lions in front of the old Vancouver courthouse and breakwaters in several areas on the coast. The stone itself splits along a couple of different grain lines, primary and secondary direction, and that in its consistent high quality and consistent composition makes it an easy stone for quarrying and used in construction. You can see here in the picture in the lower right some of these lovely split blocks being loaded on a barge. You can see the crane down there in the lower right for scale, large blocks being loaded on a barge from Hardy Island. Here's a fun picture in 1915 of the Hardy Island quarry crew, a bunch of tough-looking characters working the quarry back in the early 20th century. And then a fairly recent view, upper right, overview of the island itself and the quarry from water side, and you can see the nature of the quarry sitting out on that little peninsula. Let's now go into a little bit about the geology of the Pacific Northwest granite. And let's begin by having a quick review of the three major rock types: sedimentary, metamorphic, and igneous. Sedimentary, as you recall, is layers of sediment consolidated. Metamorphic can be altered sedimentary rock or igneous rock. And igneous is what our granite is, and it's formed from the crystallization of a liquid magma, usually intrusive like a granite, or it can be on the surface like a lava. Our Pacific Northwest granite is an igneous rock, and it formed underneath the earth in a couple of different time frames, like we mentioned previously. This picture here on the upper right shows a granite with its common components of quartz, amphibole, a type of mineral, and feldspar, which we referred to already. This picture of a granite, though, contains more black muscovite in it than our Pacific Northwest granite. And so our granite has more of a salt and pepper look. This has a little bit more pepper than our granite. As we discussed a minute ago, granitic rock can actually have many different types of minerals in it, and igneous rocks come in very many different styles depending upon the mineral components. Here on this table, we're discussing various types of igneous rock, all the way from the left side, granitic rocks, all the way over to ultramafic rocks. And as we mentioned a few minutes ago, our Pacific Northwest granite is a granitic, or geologically the term felsic is oftentimes used to describe our rock. Now, highlighted, you can see our rock contains a fair amount of quartz. Orthoclase, a type of feldspar, it's usually light colored with less than 15% of dark minerals. The definition or term used is granite if it's coarse grained and formed inside the earth, i.e. plutonic, and it's referred to as being rhyolitic if it's formed on the surface of the earth as a lava flow. Now, other types of igneous rock, andesite and basalt and ultramafic rocks, we'll discuss a little bit later in different presentations, but our rock today, for the sake of our discussion, is a granite containing these characteristics. If we take this table we just looked at and break it down more into specific mineralogical compositions of various types of igneous rock, we produce a graph like this, where we have our granite on the left, on the top left, going over to ultramafic rock with a little bit different names here on the far right. And on the y-axis, the vertical axis, we have a percentage by volume of the minerals that are involved in each of these type of igneous rocks. Now, I'm not going to go into detail here, but of this, you can see we have two types of feldspar called orthoclase and plagioclase, which make up our rock. We have a bit of quartz. We have the light-colored micas called muscovite, the darker ones called biotite, and a type of a complex mineral called amphibole. And the way you read this graph is you can see that here on the left, our granites contain quite a bit of mica, orthoclase and plagioclase, quite a bit of quartz, a little bit of muscovite and biotite, and a little bit of amphibole. And as you go to the right, we have less and less of that till we get way over to the ultramafic rocks, which contain no quartz at all, which is actually quite unusual. Now, one thing I should point out about our Pacific Northwest granite is that we have more quartz in our granite than we have either orthoclase or plagioclase feldspar. That gives our granite kind of the salt and pepper look that we're quite familiar with here in the Pacific Northwest. Granite, as a subdivision of igneous rock, is actually broken down itself into several other subcategories. Here we have our granodiorite, our specific subcategory for our Pacific Northwest granite. And let me just say that there's a lot of other subdivisions within granite, but we're not going to spend any time talking about those today. If now we look at the formation environment and the processes behind that formation for our Pacific Northwest granite, we have to start with a little bit of a quick review of plate tectonics. So if you recall, the Earth's surface is made up of relatively thin plates which move around and bump against each other. And when they converge or diverge or slide past each other, different types of geologic features are formed. Now, Pacific Northwest granites were formed at a convergent boundary, and that specifically was a spot where North America, the northern part of the continent of North America, collided with mostly a Pacific plate made of oceanic crust, much like we have today, that occurs all the way from the southern portion of South America all the way up to the Andes to the northwest coast. Now, one type of collision we can have in plate tectonics occurs along what we refer to as an Andean style subduction zone. And that type of style occurs across the United States, all the way from the Andes of South America to the present day west coast of the United States. Now, here in that case, we have a heavy oceanic crust whose lithosphere is diving down beneath a lighter granitic crust, in this case, the west coast of North America. And in the process, the chert and the limestone and various types of basalt and some accumulated shales and sandstones are scraped off as this plate dives underneath and are melted as the temperature increases lower in the crust. And that melting begins to slowly bubble up through the lighter crust of the continental material, where it can erupt like it did with Mount St. Helens all those years ago, but it can also form magma bodies inside the lighter continental crust of the plate it's subducting underneath. And as it cools, those lighter bodies of granite can form, like we see in Pacific Northwest Granite. And then through additional tectonic processes, those granites can be exposed and brought to the surface, like we see at both Index and Hardy Island. Now, how does a pluton, or a magma body, a body of this material that is melting off a lower plate and rising up through a continental crust, how does it actually form? Well, geologists over the years found that as one of these magma bodies cools, that various types of minerals will begin to crystallize out of the cooling liquid magma body. And what we have as a description of that is something we refer to as the Bowen reaction series. And all you really need to catch here is that as the minerals form, that these minerals form specifically at certain temperatures as the body cools. The hotter minerals like olivine and different types of calcium-rich feldspar drop out or become solid as the body cools at the early temperatures. And as it gets cooler and cooler, different types of minerals begin to fall out, including micas like biotite and different types of feldspars, orthoclase feldspar. And finally, the very last minerals that drop out are the ones that make up the lighter salt and pepper elements, the salt element of our own Pacific Northwest granite. And those are particularly rich in quartz and lighter colored mica called muscovite. Now let's take a look at the pluton in 3 dimensions as a cross section here, and gives you an idea of some of the terminologies that geologists use to describe one of these cooling bodies in the Earth's crust. And you can see down below here we have our magma, which is slowly trying to rise up to the crust, and it forms all sorts of different types of stalks and sills and dikes, and all these different types of pipes. And sometimes it can burst through the surface and form volcanoes we've talked about, or lava flows. And all these are terms that geologists use to describe the nature of the geologic body that the cooling magma formed. Now, in the case of our Pacific Northwest granite, all we can really tell for sure is it looked like it was a part of a massive batholith. See this term down here below, and maybe a stalk, a big blocky element of cooling material that came up into the shallower crust, which eventually was exposed by erosion. Let's now take a look at the global paleogeographic setting during the time when the Pacific Northwest granites were being formed. The first upper picture during the late Cretaceous, about 94 million years ago, about the age of the Hardy Island granitic body emplacement, shows a world recognizable with continents of North and South America, Africa, and Eurasia. And you can see that along the west coast here, we have this line which represents this Andean subduction type zone, which was diving underneath a North America sliver. By the way, there was a seaway here in North America at that time. And during that time, the Hardy granite, Pacific Northwest granites, were being injected into this piece of North American crust and cooling as a magma later to be exposed to the surface at Hardy Island. Now, about 40 million years later, during the Middle Eocene, we have a Earth and continents on Earth that look very much like today's, North and South America in particular. And still, you can see along the west coast of North America, we still have this line that represents the Andean subduction. And in this location, we have the emplacement of the granitic plutons, like the index one, which would represent the salt and pepper granite of the Pacific Northwest Granite for that time. And shown here too are the two locations of approximately where Washington State would form many millions of years later. Now let's look at a little bit of detail during the development of these plutons as we zoom in on the area that represents Washington State. And I'm not going to spend a lot of time on this. I'll let you read through this in detail yourself. But it was an interesting time when the subduction was occurring, forming volcanic islands off the west coast of the United States. The subduction of a subplate called the Farallon Plate was occurring, and that was producing a series of volcanoes along the old 100-million-year-old coastline of the west coast, and the emplacement of a chunk of land called Wrangellia, which includes present-day Vancouver Island, and a lot of the information that an appearance that would describe the subduction that would be occurring in this Andean style. And as you can see here, the emplacement of these magma bodies as the Farallon Plate subducted, leading to the development of both paleovolcanoes in the area and the emplacement of plutons that would have formed the Hardy Island granite millions of years later. If we jump ahead to 75 million years ago, we can see our coast still looks about the same. We have this subducting plate, now a fragment called the Kula Plate, diving underneath the western coast of the United States. The Coast Range Arc is being formed in British Columbia, producing things like the Chilliwack and Melange belts off the west coast of British Columbia, and Vancouver Island now, as part of the Wrangellia terrain, is quite prominent. This east-west trending spreading center that we talk about developing back behind in Washington State was producing some more complex elements, which would later on lead to things like the basalts of the Pacific Northwest. Finally, if we dip into what's called the Chehalis episode, about 57 to 37 million years ago, we have a west coast that still has subduction occurring here, which has appearances that would be quite recognizable nowadays, even though it was 50 million years ago. But we have this rather interesting embayment that occurred at the time, where the passive margin, the plate above the subducting Kula plate, existed, and as the subduction continued to occur both north and south along the boundary between North America and the Pacific Plate, fragments of the Pacific Plate subfragments, one called the Farallon Plate, one called the Kula Plate, were being subducted, in this case in a rather interesting perpendicular fashion under an active margin that existed in southern Washington State along this embayment and in northern California. These big basalts would later become exposed in the Olympic Mountains and would be remnants of erosion that occurred when the Olympic Mountains were uplifted much more recently. Complex plate boundaries producing complex systems, but all leading to the emplacement of these granitic bodies that formed our Pacific Northwest Granite. If we drift a little bit more into the future, we have now at the early Chehalis episode, a strong north-south strike-slip fault forming. This would lead on to other complex plate tectonic boundary issues as different basins were being formed in this region. And as I mentioned, the crescent basalts were being deposited and overlain by marine sediment at this time, which ultimately would be uplifted, forming the Olympic Peninsula, the dramatic mountains of the Olympic Peninsula. This Cascade episode now closes out about 37 million years ago with a small piece of a plate now called the Juan de Fuca plate, a fragment of the Kula plate, still subducting beneath North America, still injecting additional magma bodies into the crust and now forming a block of volcanoes that ultimately would become familiar with as our present Cascade volcanoes, extending all the way from Northern California into British Columbia. The overprint of all of this occurred over the last 2 million years with a series of glaciers coming down from northern Canada and parts of North America, flowing down through the valleys and covering some mountain ranges in British Columbia and coming down into the Puget Sound and in parts of eastern Washington. These glacial bodies eroded a lot of material off certain parts of mountain ranges, leading to exposures of some of the granite bodies we've seen in the Pacific Northwest today. And of course, they also drug down from British Columbia large bodies of rocks referred to as erratics, glacial erratics. And many of these glacial erratics contain granitic coastal mountain material, which is found on the surface today and actively sculpted by some of our own Northwest Stone Sculptors Association folks. So let's switch into modern analogs. Well, frankly, we don't have to look too far to find modern analogs because they're happening right today in the Pacific Northwest as our Cascade volcanoes, all the way from Lawson Peak through to Mount Garibaldi up in British Columbia. These are the surface expressions of earlier, deeper magma bodies being injected in the North American plate by the one Fuca plate subducting underneath. They formed granitic bodies at depth below them right now, and they've appeared as active volcanoes on the surface, including good old Mount St. Helens here in the southwestern part of Washington state. So what we would say is that modern day, over this period of time, all the way back from the late Cretaceous, 94 million years ago, to present day, a continued series of subducting plates and subplates resulted in scraping off that material, forming these magma bodies underneath North America, all the way from the Rocky Mountains all the way to the west. And present day analogs are exactly what's happening right now. So if you were to go dive down underneath Mount St. Helens, you would probably find a granitic body down there, much like either the Hardy Island body or the Index granitic body that we actively use as Pacific Northwest granite today. When it comes to art and architecture, Pacific Northwest granite is all over the place. And our own sculptors at the Northwest Stone Sculptors Association have carved Pacific Northwest granite from the very beginning of the association. A lot of our famous members like Tracy, Sue, and Pasha, as well as Verena, have created really magnificent works from Pacific Northwest granite over the years. It's consistent material, has a lot of characters and properties that make it hard to work. It's a hard stone, but it produces really pretty long-lasting forms, especially if your finalized piece really enjoys a little bit of the salt and pepper contrast that comes from the Pacific Northwest granite that we find both in the Hardy Island area and specifically in the Cascades, in the Snoqualmie and in the Index area. Architecture-wise, I mentioned Lions Gate, both in the Lions at the Vancouver Art Museum, also in the footings of the Lions Gate Bridge in Vancouver, Washington State Capitol, Olympia, and the Smith Tower in Seattle all heavily utilize Pacific Northwest granite in the construction and long-lived nature of these architectural landmarks of our area. So in conclusion, what can we say about granite from the Pacific Northwest? Well, it's a wonderful stone to sculpt, a hard stone to sculpt, but many of our sculptors over the years have chosen it to make both iconic figurative and abstract pieces of art. It's a wonderful stone in many ways, but one very key element about its geology is fun to think about, and that is the stone that we carved from 100 million years ago to 20 million years ago from the Hardy Island in the Cascade area is actually forming under our feet today in the modern Cascade Range. So it's a great thing to think about as you're working Pacific Northwest granite. that it is actually being formed probably in a very similar fashion as it was formed 100 million years ago, right underneath the Cascade Range today. Something to think about and ponder as you're working your piece and to point out to your viewers and potential buyers. Well, it's been fun creating another Geology of Sculpting Stone, this time Pacific Northwest Granite. I look forward to talking to you next time. Bye bye.